How automakers are 3D printing parts for production cars and classics. It's possible you'll be able to take advantage of the process for your own car soon. About 25 years ago, Ford took a few of us into its research center and showed us stereolithography. It was a very expensive and sophisticated process that used laser light to very precisely prescribe a shape in a pool of resin. When the special polymer was introduced to the light, it solidified and was retracted a tiny increment by a small table submerged in the liquid. Then the laser would solidify another layer attached to the first one. And so it went until a full-size plastic part emerged. In that demo, the part was an intake manifold that was structurally not very strong, but it fully duplicated the flow characteristics of the genuine metal part. Making prototypes in this fashion was tremendously faster, cheaper, and more accurate than either hand fabricating them from metal or making prototype castings. And in the case of manifolds, the process could create parts with complex internal shapes and cavities that couldn't be produced by conventional machining methods. These days, simpler versions of such 3D printers can be purchased by home hobbyists for less than $1,000 and used to create all manner of stuff. These use various forms of fused deposition modeling, FDM, to create layers by extruding plastic filament through heated nozzles. The materials vary, but they are still plastic and have limited structural strength. That, however, is rapidly changing. The Bugatti Chiron's titanium brake caliper. Bugatti recently announced that it has developed a titanium brake caliper for the Chiron that is manufactured using 3D printing. And earlier this year, Porsche said that it now has added 9 3D printed parts to its classic catalog and may soon add 20 more. So how do these 3D printers produce metal parts suitable for structurally demanding automotive applications? Bugatti uses a process called selective laser melting, SLM. It starts with a table on which there is a production plate made from the same titanium that will be used for the 3D printing. The table moves down by 60 microns, 24/10,000ths of an inch, in this case, although the increment can be as little as 20 microns, or 8/10,000ths, depending on the particular part. The table is then covered by a layer of powdered titanium, which is smoothed to a 60 micron thickness, the same as the layer increment. The powdered titanium is produced by melting titanium until it is highly liquid. It's then atomized by a compressed gas, and the tiny droplets cool as they fall and land as titanium powder. A powerful laser beam then traces the next layer, melting the powdered titanium as well as the material beneath it, essentially welding them together. Then the table moves down again and the sequence repeats, creating a total of 2,213 layers in the case of the Bugatti brake caliper. The process is fully automated, but it takes 45 hours to complete a single caliper. Once the 3D printing is complete, the part must be separated from the production plate using an electric discharge machining (EDM) process to produce a precise and clean cut. Then the material is heat-treated to remove any residual stresses and maximize its tensile strength. As you can see in the photos, certain support structures are built into the part to prevent warping during the high-temperature 3D printing process. These are removed after the heat treatment, in part using various hand tools including a dentist's drill to reach into the smaller cavities, and finished with more EDM work. Although the final part is very close to the desired finish contour, the brake cylinder bores are within 0.2 mm (0.008 in) of their final dimension, and the internal hydraulic circuits are created during the 3D printing process. 11 hours of machining are still required to finish the caliper. Frank Otzk, Bugatti's head of new technologies, explained that machining titanium is very difficult and this caliper requires long and thin cutters that are not very stiff. As a result, only small cuts can be made at slow speed, and the accuracy of the cuts must be frequently checked. In production, he expects to reduce machining time to about 4.5 hours. The finished part has the same ultimate tensile strength 1,250 megapascals, 181,000 pounds per square inch, as forged titanium. And this very large, 8-piston caliper, which measures 16.1 inches long by 8.3 inches wide by 5.4 inches thick, weighs only 6.4 pounds, compared with 10.8 pounds for the aluminum caliper it replaces. That's before the steel bridge plates and pad retainers that are common to both parts. Much of the weight savings comes from titanium's superior stiffness to weight and strength to weight ratios compared with aluminum. But some of the structural efficiency comes from the freedom to design the part with the material exactly where it is needed. The resulting finite element analysis produced a shape that almost looks organically grown. Obviously, this process isn't cheap, but when used for limited production parts, Otzk said, it results in cost reductions because of the savings in such costs as tooling and forging dies. And that ability to produce such sophisticated parts in small quantities is what makes this 3D process so exciting.